there are lots of problems that are unsolved now because our computers are limited and they cannot solve them. Well, quantum computers could change this. A quantum computer is a fundamentally new type of computer that could help us solve certain types of problems significantly faster. And today, I'm going to talk with you about the map of quantum computing. Now, MAP is actually an acronym I came up with. So we're going to talk about the milestones of quantum computing. We're going to talk about the applications and what can you even do with it. And we're going to talk about what is the power of quantum computing? Why is it so powerful? Now, before I talk about the general map of quantum computing, I'm going to talk about the map of my own personal journey in quantum computing. And I was asked to talk about why I'm here giving a talk. So it actually starts on the Earth, and I grew up in a town called Reading, and this is a nice Google Earth animation. And this was actually 10 years ago, and 10 years ago I was in middle school or primary school, and my school near Reading got invited to go to this technology camp at the local Microsoft offices. And there was a man who was talking on the future of computers. This was 10 years ago. And he told us about quantum computing. And he told us about quantum physics. And he showed us a really cool experiment to do with superconductors. Now, you may know that one of the primary technologies in quantum computers nowadays is superconductors. And I want to actually show you a video of the experiment that he showed us.
Vsauce. I'm Jake, and nitrogen is a gas until it gets really cold. Then it turns into this. Liquid. In this state, it has a temperature around minus 196 degrees Celsius. And these drops that are shooting off trailing vapor, well, they're literally boiling away into nitrogen gas at room temperature. And because
Okay, so you may have heard that quantum computers need to be really cold, colder than outer space, and this is actually one of the reasons why. So here he has liquid nitrogen, and he's cooling down this superconductor, because in order to have the superconductor properties, it needs to be very cold. And you can do some pretty cool things with it, so here is actually what happens when you cool this down.
One of the most amazing things about superconducting levitation is what you see here. Not only does the disk hover above the track, but it can hover below it as well. In fact, we can shape the track any way we want, and the disk zooms along at exactly the same height, no matter its orientation, with no friction or resistance.
Okay, so that is a superconductor, and that is actually one of the technologies that's used in quantum computing. Not that it's levitating, but the superconductor material itself. And when I saw this experiment 10 years ago, I was really amazed, and I wanted to study physics. So then I ended up going actually from Reading to Copenhagen because my parents ended up moving. So I did high school in Copenhagen in Denmark, which is not too far away from here. And there I did some research at some universities, the Technical University of Denmark, in different physics research. And then when it came to college, I wanted to go even farther away and go to MIT in the US. So that's where I did 2 years in my undergrad at MIT, and I studied physics and computer science. And there I took a quantum computing course with one of the leaders in the field of quantum computing, and I thought it was really fascinating. So I started to do some research with him. And then after 2 years of being at MIT, I actually decided to switch to Harvard. And it's only 10 minutes away from MIT, so it was quite a short distance. And I went to Harvard and then actually got my bachelor's there in physics and computer science last year in May. And I continued to do some quantum computing research. And now I moved all the way to Silicon Valley, so now I'm at Stanford, and I'm doing my PhD there in quantum computing. And I'm in my second year. And I'm also doing a NASA internship at the NASA Ames Research Center in Mountain View in California. So, so here's Stanford. Yeah. So when I was at MIT, the first research experience in quantum computing was actually a hardware quantum computer. So they were trying to build these things called ion traps. And the idea is you have an ion and you trap it actually in a vacuum. And then this ion can act as the quantum computing bits. So a vacuum is actually very important in many different types of quantum computing technologies. And right here, I actually have a vacuum with me that I shipped over, and I got a lot of TSA tape on it. But you'll see later in this talk why a vacuum is actually important for quantum computing, because quantum physics, it has to be isolated from the environment. So we want to remove as much possible interactions as possible. And as you may know, a vacuum is you're basically removing the air from whatever system you're in. So here I actually have a vacuum chamber and a vacuum pump. And one cool experiment you can do is you can actually show that you can boil water at room temperature because of the pressure. So as you remove the air, the pressure becomes lower, and therefore you can actually get the water boiling. So we're going to see if this will actually work. And I have here my phone. So, okay, twisted. But here I'm going to switch on the vacuum pump. You might be able to see it. There we go. And as you can see here, the pressure is actually decreasing. So all the air is being pumped out. And in here you see there's some water, and this water just is from a normal bottle of water. And eventually you can see there's some little bubbles forming. And then once the pressure continues to decrease, it starts to boil. So, and this water is at room temperature, so I can still touch it, and yeah. So let's stop that experiment. But that's some of the really cool physics that's going on behind quantum computing and that we're using today. So, okay. So now we're going to actually talk about what quantum computing is about. What are the big milestones? So you may have heard this recently in the news. There's been a lot of news articles out recently about this new milestone called quantum supremacy that Google and NASA have collaborated with to do. So I'm curious here, how many of you, raise your hand if you've heard about quantum supremacy? Okay, some of you. So this actually came out a few weeks ago, and Google announced this, and they've actually been working on it for a while now, so we've been waiting for it. But basically, the idea is, it was the first time that you could demonstrate that a quantum computer would outperform the world's best supercomputer at a particular task. And actually, I was at a tech conference a week ago, and the presenter of the tech conference asked me to, he basically told everyone at the conference to ask me about quantum supremacy. And one of the most common questions I got asked was, is it real? And so my answer is yes, it is real. Quantum supremacy has actually happened. Now, what exactly did this experiment do? Well, we take a quantum computer and we look at it and we compare it to a supercomputer. So they actually took the world's best supercomputer and they took a very, very specific problem. And they said, let's run this problem on the quantum computer, and now let's run it on a supercomputer. So you can think of it like a race between the quantum computer and the supercomputer. And it turned out that you could actually run this problem in just 200 seconds on the quantum computer. And on the supercomputer, they claim it would take 10,000 years. And this is a huge difference, and this is why it's so exciting. Now, there's been some other claims that maybe it's actually less than 10,000 years, and we can talk about that in the Q&A. But for now, Google has a paper published in Nature on this, and you can go read it. And a few months ago, I gave this talk, and this was the slide I had. The current state was that everything you can do on a quantum computer, you can do on a classical computer. But now, this is actually the past state, because that's not true. Now there is one exception, the quantum supremacy experiment. And you may think, okay, well, one problem, why is that useful or not? Well, you can see that we've gone from 0 problems to 1 problem. And you may think, okay, that's not a huge difference. But actually, it's really exciting, and it's really boosting confidence for the field of quantum computing. Because a lot of things, if you could think of 0 as nothing or impossible, a lot of things are like impossible, or we don't know whether they're possible or not. And now that we've demonstrated one problem is faster on the quantum computer, it gives this possibility that we can do even more problems faster on the quantum computer. And we're actually getting closer to real applications of the quantum computer. And so the next milestone, I would say, is something called quantum advantage. And this is the idea that now you can solve a useful problem significantly faster than the best classical computers or the supercomputers. So the quantum supremacy experiment, it was actually, people think it's a pretty useless problem, although people are trying to find some applications of it. But the next milestone would be to find a useful problem. So right now you can see that here we are, we're at 53 qubits, and a qubit is a quantum bit, and that's just the equivalent of a bit on a normal computer. And so with 53 qubits, we can solve one problem significantly faster than the world's best supercomputer. And this is our current state. But we actually want to get to millions of qubits. That is the ultimate goal, because we know if we could get to millions of qubits, we could actually solve many useful problems. Theoretically, we know this. And so you can see that there's a big gap in between. And in between, this is the large unknown. What happens in between is what's happening right now. Do we suddenly find more problems? And it turns out, actually, maybe we don't really need a millions of qubits quantum computer, also known as a large-scale quantum computer. And this would be really exciting, because that means that we can actually start running things on real quantum computers and applying it to industry. Or maybe it's more linear. Or maybe it's actually going to be even slower, and it turns out that this specific problem can't even be applied to any other types of problems. And I guess maybe the worst case scenario is like we make no progress until we actually have a large-scale quantum computer. So this is the large unknown, and I think this is why it's really exciting, because there's an opportunity for people to come in and take a part in this large unknown. So I actually say there's an opportunity for quantum developers here, and we actually need to develop the next quantum developers. And the great thing is that anyone has access to this quantum hardware. IBM, Google, they've actually published APIs where you can run real programs on these quantum computers. And they want to develop the next developers for quantum computing. So we have the large companies, IBM, Google, Microsoft. We have the universities working on quantum computing, Oxford, University of Copenhagen, MIT. And there are actually a bunch of startups working on quantum computing. For example, Rigetti in Berkeley, Zapata in Boston, etc. So actually, I'm curious what you guys think. I have a poll. And how many startups do you think are working on quantum computing around the world? And you can go to polev.com/quantum225 and put in your answer. And then I will display the results, and we'll see how many startups you think are working on quantum computing. Okay, so let's see. Okay, interesting. So yeah, you guys you're actually pretty on board. There are actually more than 100 startups around the world working on quantum computing. And this number has grown exponentially just in the past couple of years. So as you can see, there's a lot of opportunities, a lot of people are working on this. And some of these startups, they're just working on the hardware, for example, using vacuums or superconductors. But some startups are working on just the software. So they're trying to develop these new APIs and new ways to interact with the hardware. Okay, so we've talked about the big milestone of quantum supremacy, but now what about the applications? What could you actually use a quantum computer for? Well, as I mentioned, with the large-scale quantum computer, we know that you could solve many useful problems. So the question is, what are these useful problems we could solve if we had a quantum computer with millions of qubits? Well, let's take a look at an example. Let's say I give your computer the number 15, and I ask it, multiply two numbers you must what are the two numbers you must multiply to give me 15? Well, your computer would say, that's extremely easy. Of course, I know 5 and 3 give 15. But what happens if I give it the 617-digit number? And I ask it, what two numbers must you multiply? Actually, your computer is going to overheat from this problem. It's not going to be able to solve it. And in fact, we can estimate that it would take up to 1 billion years using the best known algorithms to try and find those two numbers. And when I say classical computer, I'm actually referring to something, a normal computer that's not a quantum computer. So that's some terminology that we use. So in a classical computer, it can take up to 1 billion years to find those two numbers. But what about a quantum computer? How long do you think it could take? So I have another poll to see what you guys think. How long do you think it would take on an ideal quantum computer with millions of qubits to find the two numbers to multiply to give that 617-digit number? Okay, let's see what you guys think. Okay, interesting. So you guys are pretty optimistic, but you're actually pretty on board. So it's around 100 seconds, which is crazy, right? We go from 1 billion years on a classical computer to 100 seconds on a quantum computer. So how are you able to do this? Well, that's because you can create a quantum algorithm. These are a set of instructions that you give to the quantum computer. And Peter Shor, who's actually a professor at MIT, created this algorithm called Shor's algorithm. And he showed that you can actually find those two numbers significantly faster than any of the best known classical algorithms on a classical computer. Now you may think, okay, two numbers multiplying, that's not a very useful problem, is it? Well, if you're familiar with encryption, yes it is, because that's actually what encrypts your data on the internet. You can think of those two numbers as a key. As long as no one can find those two numbers, you don't have the key to unlock all your data. But with a quantum computer, you essentially have this key now. So you could unlock and decrypt all of this data. And this is actually, one of the reasons why a lot of people have been excited about quantum computing or worried about quantum computing, because it could potentially break a lot of the encryption systems out there. So do you need to worry or not? Well, first of all, it is something we should think about now, because it could take, who knows, maybe 10 years to actually change all of our systems, to re-encrypt them to new systems. And at the same time, there's this thing called store now, decrypt later, where people could actually store your data now, and then maybe when there's a quantum computer, they could decrypt it later. So it's important for us to start thinking of new encryption systems to keep our data secure. But you don't need to worry, because as I said, you would need a quantum computer with millions of qubits to actually run this algorithm. And so far, we only have 53, so we're not there yet. Now, another problem is chemistry, and this was actually the initial proposed solution for a reason why we need quantum computers. Because basically, the world out there is made up of atoms and molecules, and they all follow the laws of quantum physics, which basically describes the way these atoms and molecules behave and how they interact with each other. And that's what a quantum computer is. It is these quantum particles, and they interact with each other. So the two naturally map together. You can use a quantum system, which is a quantum computer, to simulate and understand a quantum system. So the idea is we could simulate molecules and atoms more efficiently. Now, what would that enable us to do? Well, we could potentially design new types of medicine, because medicine is just basically, these drugs are just molecules, and they interact with other molecules in your body. And we want to understand what happens when these react. And so that's why a quantum computer could potentially help us to design new medicine. We could also potentially design new types of materials. And again, materials are made up of molecules, so you just want to understand how they interact and how they give rise to certain properties. Now, these two problems, simulating chemistry and finding the prime factors of a large number, we know that a quantum computer can solve it exponentially faster than any classical computer. So what do I mean by that? Well, let's say you had your phone and you only have one digit to enter for your passcode. Well, that would be extremely easy to crack. You'd only have to do 10 tries. But what happens now if I have 4 digits? Well, now you'd have to do 10,000 tries to try and crack the code. But now, if you have 6 digits, it would take 1 million tries. So this is an exponential problem, right? Because as the size of the problem only increases from 1 to 4 to 6, the time to solve it scales exponentially. And a quantum computer could help us with some of these problems by actually only scaling polynomially instead of exponentially. And so you can see that a quantum computer is especially useful when the size of the problem is larger. Now, I can't be at a software conference without mentioning machine learning or AI, and quantum computers could actually be applied to machine learning too. Now, you may think, so there's a field called quantum machine learning. You may think, oh, this is just a bunch of buzzwords together. Is it actually real? Well, actually, if you look at the underlying mathematics, it does sort of make sense to apply quantum computing to machine learning. Because if you're familiar, machine learning deals with vectors and matrices in a high-dimensional space. And actually, quantum computing is also just vectors and matrices in a high-dimensional space. So the underlying mathematics is very similar, and you can map the two problems together. And the idea is, we know that we've made progress in AI now because of the more powerful computers we have today compared to many years ago. So maybe if we had a quantum computer, that could bring forth a new wave of progress in artificial intelligence. Another problem is unstructured search. So to illustrate this, I actually have a bag with 100 balls. So let's say I ask you, find me the ball number 3. Well, you'd have to basically pick up one ball and continue until you find the ball number 3. And this is how our computers solve basically a lot of unstructured problems. Because there's no structure, you have to just brute force your way, finding one by one by one. So if you had 100 balls, that would obviously take 100 tries, up to 100 tries to find the ball you want. But what about a quantum computer? Even when there's no structure, how many tries do you think it could take to find a certain number? Well, actually, it could take just 8 tries. And so this isn't exponential. This is actually a quadratic speed up. So not everything has to be exponential speed up in quantum computing. But as you can see, you can generalize this. So if you had n balls or n entries in a database, let's say, then classically you'd have to do up to n tries. But in a quantum computer, you can actually do it in square root of n. And unstructured search is such a general problem that this could be applied to a lot of industries and a lot of problems. And how are you able to do that? Well, again, there's a quantum algorithm. And a guy called Grover created this algorithm called Grover's algorithm. And later in this talk, we'll actually see how you can implement this and program this on a quantum computer. So you can see all of these applications in factoring, simulations, machine learning, search. And these applications are so broad that they could be applied to a lot of different industries. For example, artificial intelligence, medicine, materials, or maybe even finance, space, and logistics. And this is what could happen if we had a quantum computer with millions of qubits, a large-scale quantum computer. And that's why people are really excited about it, because it could unlock basically all of these problems we've never been able to access or never been able to solve. So we could solve the unsolved problems potentially with quantum computers. So you may be asking, okay, this sounds great, but how is it actually able to do this? How can it be better than the world's best supercomputer? Well, now we're going to talk about the power of quantum computing. What gives it its power? And basically, the short answer is quantum physics. So your classical computer works by classical physics. It works by bits, zeros and ones. But in quantum physics, those rules don't apply. There's more strange behavior and rules. And actually, one principle we'll look at is called superposition. So to illustrate this, let's remember again, you can write any character as a sequence of bits, zeros and ones. And let's say we have a classical bit. Let's say 1 is the frosted side and 0 is the plain side. So on your normal computer, it basically just goes 0, 1, 0, 1, 0, 1. But a quantum computer has something called a quantum bit. And it can be 0, it can be 1, but it can also be a superposition of 0 and 1. And I think of this like a spinning donut. Now, if I ask you, is it 0 or 1? You say, well, it's kind of a combination of both. And so this superposition can be very powerful. So let's see exactly why. Well, let's say I give you a donut box, and there are 2 donuts in it, and I ask you, oh, you can't see the box, but I ask you, what do you see? Well, either you see plain, right, 0, 0, or you see 0, 1, or you see 1, 0, or you see 1, 1. But now, if I give you a box with 2 quantum bits, and they're spinning inside this box, I ask you, which combination of states do you see? Well, you say, I see all of them at the same time. And these are the states or combinations of these 2 quantum bits. So actually, that's the power of quantum computing, is that you can process multiple combinations or states of bits simultaneously. And now I have another question for you, and you may have to do a little bit of maths, but how many combinations will there be if you had 300 qubits in superposition? So let's take a poll. Okay. Interesting. Okay, so you guys just went with the largest answer. But actually the correct answer is 10 to the power of 90. And basically it's just a little bit of maths, but as I said, when you have n qubits, when you have n qubits, you can actually be in 2 to the power of n possible states or combinations. And we had 2 to the power of 300, which is roughly 10 to the power of 90. And this is actually more atoms than there are in the observable universe. So the number 10 to the power of 90, which is crazy. So that's why you can get a lot of power with superposition, because you can process all of these bits and all of these combinations simultaneously. So you may ask, well, okay, we have this superposition, but how do you actually operate and control the quantum computer? Well, how do you operate a normal computer? We use something called logic gates. So for example, you have the NOT gate, which takes a logic from 0 to 1. And then this is how you build a computer. You build basic modules, a chip, a circuit, and then you have your computer. So it's actually similar in quantum computers, except that we have quantum gates instead of logic gates. So for example, we have something called the bit flip gate, which is actually equivalent to the NOT gate. So you put it through this gate, and then it ends up flipping it to the other side. And this is called an X gate or a bit flip gate. And then we have something more special called a Hadamard gate. So let's say it's 0, and you put it through the Hadamard gate, it actually ends up putting it into superposition. So you can see that we have more special types of gates than just normal logic gates. And what you can do is you can combine these quantum gates together to build a quantum circuit. And the goal is that you can execute a quantum algorithm with these quantum gates. So I said a quantum algorithm is a set of instructions you give to the quantum computer. So you basically have these sequence of quantum gates. And the goal of the algorithm is to use these quantum effects, such as superposition and other quantum effects like entanglement, which you may have heard of, to solve a problem faster. So let's take a look at an example. So let's go back to Grover's search, which is actually the one with the ball example. And in this case, we're only going to have 4 balls to simplify the problem. But let's say I ask you, find me the ball number 3. Well, classically, that would take 4 tries, up to 4 tries. But on a quantum computer, you could actually do this in just 1 try. So here you have the numbers, and you convert it to bits. And we want to find 1, 1. So this is actually the quantum circuit that you would need for Grover's search. And as you can see, you've seen these gates. Here we have the Hadamard gates and the X gates. And you can see it's just a sequence of steps in order to find your problem. And there are other special gates and measurements that we haven't talked about, but you can read more about that. And so this is actually how you implement things on a quantum computer. And this allows you to program a quantum computer or code a quantum computer by using these quantum gates. So yes, you can program a quantum computer by using the quantum gates. So let's take a look at an example. So IBM has this cool thing called the IBM Q Experience, and you can look this online. So you can visually see these gates. And here in this case, I'm taking the Hadamard gate. And you can see we have these different lines, and each line corresponds to one quantum bit. And so in this case, you can basically drag and drop the gates, and we can hit run, and you can see that it says, okay, it's actually sent this to the real quantum computer. So if you wanted to, you can actually send a sequence of instructions to a real quantum computer, and it does it through the cloud, and they'll email you back with some of the results. And if you wanted to get more complicated code, you can actually write some code in Java or in Python, for example. So here is the Strange API, which is a Java API for quantum computing. But here's some very simple code that you can write to actually implement a quantum circuit. So here we're just implementing a method, the quantum circuit, and then we're basically creating the simulator. And when I say simulator, what happens is, remember that in quantum computing, underlying mathematics is actually just matrices and vectors. So you can actually simulate what a quantum computer would do on your computer by just multiplying matrices and vectors. Well, you say, well, what's the point of the quantum computer then? The thing is, these matrices can get really, really large, so it can be very inefficient, and it will be extremely slow on your classical computer. And that's actually why in the quantum supremacy experiment, we needed to get to 53 qubits to actually demonstrate something faster than the world's best supercomputer. Because if you only had 10 qubits, you could actually just simulate that on a computer and it would find the result. But once you get larger with the number of qubits, it's harder and you can no longer simulate it because the matrix the matrices get too large and it gets too complicated for your computer to solve. So here we have the simulator, and then in this case, this is just the syntax of the API, but we're creating a program, and we're actually creating one qubit. And then, as I said, an algorithm, you have these set of instructions, so we're going to call these steps. And then basically, to these steps, we're going to add the Hadamard gate. And you can see it's very simple. We just say the Hadamard, and the 0 means that we're applying it to the 0th qubit, and we only have one qubit, so then we basically add these steps to the program, and then we can get our result by running it on the simulator. So as you can see, you can actually code on a quantum computer, and there's also APIs in Python and other languages that so you can get started with this right away. So you may ask, well, how do you actually build a quantum computer? What is this actually running on? So if we look at how do we build our normal computers, well, we have transistors, as you know, and we need something that acts as zeros and ones, right? We need something that can be a bit. So in the transistors, it blocks, it's very simplified, it blocks and allows the flow of electrons to act as the zeros and ones. But it actually didn't used to always be this way. They used to use vacuum tubes way in the past, and it turns out that transistors ended up being more scalable, easier to use, so that's why we use transistors today instead of vacuum tubes. But I show this analogy because it's actually the same in quantum computing. There are actually different ways to build a quantum computer, but we're not really sure which way is the best way yet. So I've mentioned, and we saw the cool video, that you can use superconductors to build quantum computers, and this is actually one of the most popular ways at the moment. This is what Google and IBM and the startup Rigetti are doing. And I also mentioned you can use trapped ions. So that was the case when you have an ion trapped inside a vacuum. You can also use photons, which is light. You can even use diamonds. And I actually have a friend at Stanford who is working on diamond quantum computing, and he said, yeah, if you ever need any diamonds, just let me know. I was like, yes, please. So as you can see, there's many different ways to build a quantum computer, and it's a really exciting time because we're not really sure which way is going to be sort of the equivalent of the transistor. So at the moment, superconductors are the ones that are most popular, so it may be superconductors, but maybe there's a new technology that we're not aware of that could come and make it so much easier to build a quantum computer. So you may ask, well, why don't we have a quantum computer with millions of qubits? Well, there are a lot of challenges to build one, and I like this analogy of spinning because just in the real world, if this is spinning, eventually it will actually stop spinning. It's not going to keep spinning forever. And remember, the spinning represents the superposition. So it's just the same with a quantum bit. If it's in superposition, it actually can't stay in the superposition forever. It eventually loses that quantum effect, and it eventually just ends up being 0 or 1. And we need it to be in superposition to be able to process it faster. And it's a real challenge to control these quantum systems because in order for it to be spinning forever, it actually needs to be isolated. Because you can imagine that atoms and photons in the air come and they basically hit and interact with it, and it loses its superposition. So that's why, for example, a vacuum is important in a lot of quantum computers, because when you have a vacuum, you're removing all of that air and you're removing all of these other particles that could interact with the system. So it's a big challenge to build quantum computing, but that's why the quantum supremacy experiment by Google is very exciting and a big engineering achievement, because they were actually able to control a quantum system and make it do operations that we can control. And so I mentioned this is why a vacuum is important. So to conclude, what are people working on? What is there left to do in quantum computing? Well, I came up with another acronym, MATHS, and we're already seen this. So the milestone is to outperform the best classical hardware running the best classical algorithm for a particular problem. And we've actually already done this, which is exciting, but now we need to do this for a more useful problem. So we need to keep hitting these milestones. Then we need to continue to find new applications for quantum computers. As I mentioned, this is a great opportunity for developers who are interested in quantum computing, because we really need people to think of how can you design new algorithms for the limited quantum computers we have right now. Then there's a lot more theory that can be done. There are a lot of theoretical computer scientists who are looking at how can we prove that there are problems that are hard to do on a classical computer but easy to do on a quantum computer. Then we have the hardware, so we need to increase the number of qubits, but actually the number of qubits isn't all that matters. What also matters is the quality of the qubits. As I mentioned, how long can it stay in superposition for? And there's also some error in the quantum gates that we mentioned. So maybe, for example, it doesn't always flip the bit. So we need to continue to decrease those errors. And then finally, we need a shift in our mindset from the classical realm to the quantum realm and think, how can we rethink of how we think about quantum computing? And actually, Peter Shor, who created Shor's algorithm, which is the one that can break encryption, he wrote a paper quite a while ago saying why he thinks there haven't been more quantum algorithms being designed. And he said, well, computer scientists think classically, right? We think classically. So it's hard to think in this quantum realm. And there's a lot of cool things like education, things to try and increase people's knowledge of quantum computing. So for example, there are some games like quantum chess that you can play. And there's a lot of hackathons that go on around quantum computing to get more people to think about this and to design these new algorithms. So far we've seen that you can solve some problems significantly faster on a quantum computer. And this could help us potentially understand nature more accurately. And if we could understand nature more accurately, we could design new medicines, and we can maybe advance artificial intelligence. So I think there are two future states of the universe, one with no large-scale quantum computer, the one with millions of qubits, because maybe there's some big engineering challenge we can never achieve. And there's one state of the universe where we will have a large-scale quantum computer and where we can solve all of these amazing problems I just talked about. And right now, we're in a superposition of both. We don't know which one is going to be happening in the future. But as a researcher and as a quantum developer, our goal is to break that superposition such that we have a quantum future. Thank you.